Hey, today we're going to solve a simple problem using linear momentum equations in fluid mechanics. And the actual linear momentum equation we're going to use is a variation of Reynolds transport theorem, which I'm going to assume you at least have a little bit of prior knowledge about, just so I don't have to go into the theory so much, but rather the application. Okay, so to solve this kind of problem, basically you're going to follow this kind of algorithm. The first thing you want to do is define a control volume for the problem. After that, you want to identify control surfaces. Then after you've done that, make some basic assumptions about the flow properties that are occurring within the system. After that, identify forces. That's particularly important because we're doing linear momentum. So you want to look at the external forces on the system, like the pressures, and the internal forces, like normal forces or reaction forces for elements within the system. After that, want to set up Reynolds transport theorem, perhaps use the continuity equation to help simplify some things. And after that, you simplify what you have and solve the system. That's a bit much to throw at you all at once, but you'll see it starts to make sense as we start going through the process. So again, the first thing we want to do is we want to identify our control volume. And that just means we're going to put a big box around what we think our system is. If you're looking at a larger problem, it's a little trickier to identify our control volume. But here, we pretty much zoomed in on the system already. So this will be our control volume. It's basically like if you have a reactor, how usually you draw a box around it and then look for the inlet streams and the outlet streams. So that's what we're doing here. The next thing we want to do is we want to identify the control surfaces. That's basically where you have flux of dependent properties in the system, so I'm going to assume it's steady state. What that means is time dependent properties go to 0, so time derivatives go to 0. The other assumption I'm going to make is that the flow within here in the system is going to be incompressible. That means is that density is constant. You'll see how these two simplifying assumptions really help us later on when we're solving Reynolds transport theorem, as well as the continuity equation. Okay, the next thing we need to do is think about the forces that are exerted on this system. So one of them is the one that, if you've read the problem statement, what we're looking for, and that is the force of the bolts. So this is an internal force in the system. It's the bolts basically keeping this nozzle together as water flows through it. The force we really need to worry about, which I'll sort of indicate in periwinkle, or try to, is the force of pressure. So as this nozzle is sitting here in the air, like all objects, the air is pressing up against it. The air particles are bouncing up against here, normal to the surface of our object. Okay, the important part is that if you look at the top and bottom of this nozzle, all of these air particles are pressing up against it with the exact same force. The angle depends on the surface, but you can see that there is symmetry here. So we don't really need to worry about the pressure on the top and the bottom, or rather the sides, because we have to remember this is a cylindrical geometry. What we need to worry about is over here. So we have pressure going in like this, and we have pressure going in like this. And as you can see, the inlet is larger than the outlet. So there is most likely going to be some sort of pressure difference between the left and right hand sides of this system. And that's what we see up here in the problem statement. They're telling us that the initial pressure is 159, and they're saying, okay, call the second pressure 0. This is something you'll find a lot. It's called gauge pressure. So that's, say, if you have on the left a 400 bar pressure and on the right a 100 bar pressure. Well, you know that the difference in the pressure, the differential pressure across your entire system is going to be 400 minus 100, so that's 300, and then you basically simplify it by calling the left-hand side 300 and the right-hand side 0. That just helps you simplify the left-hand side of your Reynolds transport theorem later on. You'll see that I'll point it out again, so don't worry too much if you don't really understand that now. Okay, so after we've done all this setup stuff, we could actually start thinking about solving the Reynolds transport theorem for linear momentum. So the first thing we should do is we should look at the definition of Reynolds transport theorem. So that, hopefully you've seen before, that looks like this. And the beta that you see hanging around is sort of a general parameter, a general explicit parameter that could be, well, it could be several things. It could be mass, it could be momentum, it could be angular momentum, it could be energy. In this case, we're going to say that beta is going to be linear momentum. So this is what we're choosing. Okay, so you see on the left-hand side, that just means there's going to be an mv over here, but on the right-hand side, this is beta over m. So the m in your momentum will cancel out, and you're just going to get a v over here and another v over here. And that's going to make the equation look like this. Okay, don't worry about these two guys over here on the right. We're going to get to them and explain them in a little bit more detail, but just take a look at this on the left. You should have seen something like this many times in your introductory physics course. Of course, you know that the mass of the system is going to be constant if we're doing this steady state. So what that means is that you could pull this mass out of the differential, and you're going to have m dv dt. If you remember back to your introductory physics, that is simply ma, and what you can do now is use Newton's laws to make this statement. Basically, if we're looking at m dv dt, we're looking at the change in acceleration of our system. So that's basically just saying this on the left could be equated to the sum of the external forces and the internal forces of our system. And those forces we were talking about earlier are going to be the pressure on the left, the pressure on the right, which is equal to 0, and that internal pressure of, well, the internal force of the bolts. Okay. The other thing we should sort of mention is that we made the assumption that we're working steady state. What I said earlier is that meant that the time derivatives equal 0. So over here, in these two terms here, the scary looking integrals over here, we do have a time derivative in the control volume term. That's the one over here. But since we're working with steady state, we know that this term will go to 0. That simplifies things a lot. We're going to see this term come up later when we do sort of unsteady state problems. That means you have something like an empty barrel being filled over time with some sort of material, or you have a full barrel being emptied over time by some sort of outward going flow. But here we're just working in steady state. We don't have to worry about that so much. The one we do have to worry about is over here, where you see the CS, that stands for control surface. So for each control surface that we have in the problem, we are going to get an integral. What that means is that this term will actually expand into two terms. One over here for what I'm going to call in, and one over here which I'm going to call out. Okay, let's do this a little slowly since we're doing it for the first time. We're going to have the forces on the left-hand side by using Newton's second law. and that, again, is going to be the pressure on the left, the pressure on the right, and the internal force of the bolts. What you need to be a little bit careful about is the sign convention over here. So you'll see that the inward pressure is positive and the outward pressure is negative. The reason for that is what I was saying before. When you're working with pressures, that means you have air pressing in to the object or system you're looking at every spot. Now on the left, that means that the pressure is going rightward, which we defined as positive, and on the outlet side, the pressure is facing inward, so that means it's going left, which is negative. That's why you see over here this term is positive and this term is negative. The other thing you need to worry about is making sure that your equation is dimensionally homogeneous. What that means is that if you're adding these terms, they need to have the same units. So that's why our force is in newtons. When we're working about pressures, we need to use that area, because remember, pressure is force divided by area. So force is pressure times area. So whenever you're working with the pressures, don't just start adding forces and pressures. That's a common mistake. Make sure always to have the areas along with your pressures, because that'll get you newtons, newtons, and newtons. Okay, so what about on the right-hand side with those control surfaces? That's going to get us two different integrals, and they're going to look like this. Like I said, we're going to have one for the inlet and one for the outlet. Okay? So another thing to at least be a little bit concerned about here is that not only do our dimensions need to be homogeneous, but you can't add a vector and a scalar. You could add a vector and a vector, or a scalar and a scalar, but it doesn't make sense to add a vector to a scalar. So if this is a vector, then this needs to be a vector, and this needs to be a vector. Same for the things on the right-hand side of the equation. This first term needs to eventually come out to be a vector, and the second term needs to come out to eventually be a vector. You should be a little worried because there's 3 vectors over here. Okay, well, we don't have to worry that much. Why? Well, if you take a look at this dot product over here, you should remember something from when you took vector calculus or multivariable calc, and that's if you do the dot product of 2 vectors, you're going to get a scalar. Hold on a sec. Just need to pull something up. That comes from this. So remember, if you do that, that means you're going to have the dot product of 2 vectors giving you magnitudes, which are scalars, times the angle between the 2 vectors. We'll worry about that in a little bit. That gets a little complicated as well, but just know that after performing this computation, you get a scalar, and then of course a scalar times a vector will give you a vector. So at the end of the day, this term and this term will both be vectors. Okay, the other thing we need to talk about is this n vector over here. So this guy is what we call a unit vector. Now you should know what a unit vector is by now. It is a vector with length 1. The other important thing is that this guy is normal to the area that we're looking at. So if we're looking at the inlet area, this normal unit vector is going to be of magnitude 1, and it's going to point away from the surface. The reason this is important is because it goes into this cosine theta we're dealing with over here, which will eventually determine whether our term is positive or negative. This might be a little confusing, so I'm going to go back up to the picture and show you what I mean. So know that we have the velocity of the flow of this water going through, that's a vector, and we have this unit normal vector of the surface. So again, this purple line over here on the left is the vector corresponding to our water, and I'm going to add a green line, and this is going to be the normal vector at these 2 surfaces. So remember, for the normal vector, it needs to point away from the surface. So at the inlet over here, it's going to go leftward, and at the outlet, it is going to go rightward. Okay, well, what about the cosine of the angle between the water flowing through and the normal unit vectors? Well, if you take a look on the left-hand side, the unit normal vector is going left and the water is going right. What that means is they're going in opposite directions, which is cosine of 180 degrees, which means that your sign will be negative. On the right-hand side, we have the velocity of the water going rightward, and we have the unit normal vector going rightward. They're pointing in the same direction. That means you're going to get cosine of 0 degrees, so you're going to get a positive term over here. So once we've done that, looking at that simplification, what we get is this. So again, this velocity is constant in respect to the coordinates we're looking at. This gets a little bit complicated. I'm not going to go into that so much right now, but also since we made the assumption that our density was constant, that could also be pulled out of the integral. So these two terms get pulled out, and this dot product gives you the magnitude of the velocity. And for the inlet, we said that would be negative, and the outlet, we said that would be positive. Okay. Over here, there's no real changes. We just eliminated the second term because remember, we were told from the problem statement that the second pressure is 0 because we're using a gauge pressure definition. Okay. So this magnitude and this magnitude are also scalars, so they're constants, and they can be pulled out of the integrand. What that means is that you simply have the integral over the area of dA, which is simply going to be the area. So the integral over here will give you the area of the inlet, and the integral over here will give you the area of the outlet. So we move this over to the other side, and this is our final equation for the force of the bolt. Okay, so a few comments here. Notice we have a scalar velocity and we have a vector velocity. And over here we have a scalar velocity and a vector velocity. That's necessary because we need all of these to be vectors to be, well, dimensionally homogeneous. Again, you can't add vectors and scalars. You need to add either all vectors or all scalars. The reason I like to keep things in this form, rho v a v, is that you could see your sort of transport definitions that are important directly out of here. So from this VA, that's what we call in fluid mechanics a Q, or a volumetric flow. And that is going to be in meters cubed per second. And this rho over here, rho VA, is going to be your mass flow rate, m dot. So you also notice that that equals rho times Q. So that's mass flow. So if you condense these terms, rho VA, what you're seeing is your mass flow times the velocity of the flow at that point. So it's mv, literally your change in momentum due to the fluid moving through the system at that point, at that surface. Okay, so how do we actually get to solving this problem? We're looking for this. We're told the inlet pressure. We have the diameter at the inlet, so that's going to tell us the area here. Remember that this picture we're looking at is a cross-section. It's an oversimplification of the geometry. This inlet is really circular, and this outlet is circular, and the entire pipe is cylindrical. So the area we're going to be looking at is really going to be pi r squared. So that's equivalent to whatever the diameter is divided by 2 squared. Okay, so we're told d1, or d in, so we know the area here. We're told the density. We're told the outward velocity. We have the diameter of the outlet, so we have this term. The only thing we don't know is this inlet velocity. Okay, so this is a problem that usually comes up in linear momentum problems. You're stuck with one variable that you don't have, and there's really only one good way to get it, and that's back up to here. We used the linear momentum equation, but we didn't solve the Reynolds transport theorem for mass, which is the continuity equation. So over here, if we say that beta equals mass, then we could do a little bit more problem solving. So that gets us this appearance of the Reynolds transport theorem related to mass conservation. And again, we use the same assumptions. We say that, okay, steady state, time derivative is 0. And we also say that mass is conserved. So we're invoking conservation of mass, and that tells us that the change of mass in the system over time must also be 0, which seems like a pretty reasonable assumption to make. So at the end, that means we just have to worry about these two control surface terms. Once again, we're going to have 2 of them, and the equation will look like this. I'm going to scroll down because I have a lot of information. Just like before, we simply have this and this. The dot products will be the same. This one will be negative, this one will be positive, and we could cancel out the rows because they're in both terms, and then we have a 0 over here, so we could simply divide by row, and we get this equation down here. Get used to using this, because this appears all of the time when you're solving these fluid mechanics problems. So that simply means, since we already know the inlet area, the outlet area, and V out, we could solve for a ratio and substitute this back in. So we now have 2 equations, 2 unknowns, our system is defined, and we could solve the problem. I hope that wasn't too confusing. Hopefully it helped, and yeah.